So this video is going to be about tensions and basically objects at rest when there are multiple forces acting on them, and those forces are at angles. Okay? So in this first example, we have a box of mass M that is at rest and it is being acted on by two different ropes or strings. Okay, so our free body diagram for that mass is going to look like a force of gravity pointing straight down. We have some tension 1 that is pulling to the left, and then some tension 2 that is at an angle. Okay. Now, we're not moving in either direction, so it doesn't really matter what we call red or green. So let's just use green in the x direction and red in the y direction. And it looks like T2 needs to be broken up into components. Okay. So we have FG pointing down, T1, then we would have T2X and T2Y. Okay, so where those tensions are coming from, T2X and T2Y, just as a reminder is if this is T2, that makes T2 our hypotenuse. Okay. To find T2X, that's how far T2 pulls to the right. Okay. So that makes this side, based on where the angle is, the adjacent side. So that means we need to use cosine to figure out what T2X is. So that tells me that T2X is T2 times the cosine of theta. And then in the y direction, okay, T2y is that vertical side of the triangle, which is the opposite side. Okay, so that means I need to use sine of theta because I have opposite and hypotenuse. T2y over T2, so T2y is T2 times the sine of the angle. Okay. So FG, T1y or T2y are in red, and I'm just color coding to make my equations easier in the long run. And there's that. Okay. So then we want to write net force equations for both the x and y direction. Now, because this mass is at rest, both the x and y direction are going to equal 0. So I have T2x pointing to the right, T1 pointing to the left, so they subtract. Again, T2x is T2 cosine theta. And if I add T1 to both sides here, you see that those two need to equal each other. And then in the y direction, I still have to equal 0. So I have a T2y minus an FG, 0. T2y is T2 sine theta. I could add FG to both sides here. So I get T2 sine theta is really, FG is the same thing as the mass times acceleration due to gravity, so I could write it like this. So depending upon what the problem is asking for, you can solve with these two equations from there. So where something might get a little bit more complicated is an example like this, where we have one mass, let's call this mass A, another mass B, and mass A is hanging by two different angles, and then we have mass B hanging straight down. So we have two different objects, so we will need two different free body diagrams. Okay, so we're going to have an A free body diagram and a B free body diagram. Okay, my A free body diagram looks like T2 acting at theta 2 and T1 acting at theta 1. And just in case it's not obvious, from my drawing, theta 1 is going to be greater than theta 2. Also acting on mass A, we have a downward force of gravity of A and a downward tension T3. Okay. So T1 and T2 need to be broken up into components very similarly to the previous example because we're given angles with the horizontal. Okay. T2x points to the right. T1x points left because I would describe T2 as pointing up and to the right, but T1 up and to the left. So that's how I know the left versus right direction. Both T1 and T2 I would describe as pointing up and either left or right. So both of their y components are going to point upwards. And T1y, T2y, and then FGA and T3. Okay, so some things I want to talk about before we move on to the tension or the free body diagram for B. First thing is whenever you have an object that is pulled by tensions at either or at two different angles, whichever one has the larger angle with the vertical, so in this case, theta 1 is greater than theta 2, that tells you, I said angle with vertical, I meant angle with horizontal. That tells you which tension is larger. So T1 is going to have a larger value than T2. Yes, parts of T1 and T2 might be the same, but T1 is going to be larger than T2. Okay. The reason why is because T1, because it is at that larger angle, necessarily needs to have a larger vertical component than T2. Okay. Now, if you're looking at your free body diagram, you might notice that I already drew in T1y and T2y like that. Okay. Now, if you're looking at your free body diagram, you also might notice that T1x and T2x need to be exactly the same. They have to balance each other. So for two triangles with the same horizontal base, okay, but one vertical side longer than the other, the one with the larger vertical side is going to have the larger hypotenuse. So think about it this way. If you're doing a squared plus b squared equals c squared, which is how we would find the hypotenuse for two different triangles, if A is the same, but B1 is greater than B2, then necessarily C1 is going to end up being bigger than C2. Okay? So larger angle with horizontal means larger tension. Now, I drew in my angles down here. Okay? You might also see problems where the angles are given up here, which if you remember through geometry, those end up being alternate interior angles, right? You look for the Z, and alternate interior angles are equal. Okay? Now on to letter B. Okay, letter B, or mass B, is a lot easier. Mass B just has T3 and an FGB. Okay. So let's say in this problem we only knew the value of mass B. We did not know mass A, and we needed to find the values of T1 and T2. Okay. So naturally we need to start with some net force equations. Okay. So for A, in the x direction, we're going to equal 0 because our masses are at rest. I already talked about this before, but T2x and T1x are going to end up equaling each other. And you might be thinking, oh, well, then doesn't that mean that T1 and T2 are equal? But that is not the case because remember, we have those cosine components in there as well. And if the angles are different, then our cosines are going to be different. Okay, then in the y direction for mass A, again equal to 0, we have T1y and T2y pointing upwards with an FGA and a T3 pointing downwards. Okay, all right. So we don't know a couple of different things. This is T1 sine theta 1 plus T2 sine theta 2 FGA minus T3 is 0. Oh, I lied. We actually do need to know the mass of A in order to solve this, which is fine. Say we know both of that. Okay. Well, it looks like in order to solve for T1 and T2, I need a third equation because I don't know what T3 is. So that's when I would go to mass B and look at the y direction on mass B. And I would get T3 minus FGB 0. So T3 is FGB, which is just the mass of object B times G. So T1 sine theta 1 plus T2 sine theta 2 minus MAG minus MBG 0. So now I have two equations and two unknowns, where T1 and T2 are my unknowns because I would hopefully know theta 1 and theta 2. So just like we've talked about doing in class, we need to rearrange one of the equations for tension. So remember, this T2 is the same as this T2, and this T1 is the same as T1. Okay, so I'm going to rearrange this equation for T2. T1 cos theta 1 over cos theta 2, and then I can take this equation and plug it in for this T2 there. Now, what's really tricky is we got to remember that the subscripts are important, so we got to watch out for like sine theta 1 versus sine theta 2, or cosine theta 1 over cosine theta 2. So this is cosine theta 1 over cosine theta 2 times the sine of theta 2 equals, and I'm just going to move these over to the other side since I'm solving for T1. So this ends up being MBG plus MAG. Excuse me. So T1 sine theta 1 plus. Now, this really could be looked at as T1 cosine theta 1 times sine theta 2 over cosine theta 2. And remember, the sine of theta 2 over the cosine of theta 2 is really the tangent of theta 2, which really for this doesn't matter. It just makes the equation look a lot nicer. MAG. All right, we're solving for T1, so we have to factor out a T1 from both of these. So sine theta 1 plus cosine theta 1 tan theta 2 is MBG plus MAG. Then I would divide both sides by this whole thing. And I get an equation for T1 plus MAG over sine theta 1 plus cosine theta 1 tan theta 2. Okay. Which is my answer for T1, and once I plug in numbers, I could then use that to find my answer for T2. And that is all we need to know for tensions at angles.